Alright, let's take a look at sample problem 6.02. We've got a vehicle sliding to a stop due to friction at the tires. So it's got some initial velocity at 10 meters per second, moving to the right, let's say, and it is going to slow down due to the force of friction at the tires. It's acting on 4 tires, but we can just sum all those up and call it the force of friction. First, let's look at a dry horizontal surface. We're going to use mu k as 0.6. That's a good estimate for rubber from your tire and a dry, like concrete road. Then we're going to change the coefficient and make it ice and see how far it takes to stop, or how long it takes to stop. And then we're going to put that on an incline. So let's do all these scenarios. On a dry, flat surface, how far does it take to come to a stop? Let's do that one first. Number 1. Well, if we do a free body diagram, we should always do a free body diagram. We see mg going down, we got some normal force going up, and the only thing in the x direction is the friction impeding our motion. So if I sum the forces in the y direction, I get the mass times the acceleration in the y, but it's not coming off the surface, so that acceleration is 0. I get the normal force is equal to mg. We're going to need that. So hold on to that for a second. If I sum the forces in the x direction, I get the mass times the acceleration in the x. Now all I have is a force pointed backwards of friction, and that's going to equal our mass times the acceleration in the x direction. We can substitute the fact that the frictional force is equal to mu k times the normal force. Put this in there, excuse me, and I get minus mu k times the normal force is equal to mass times the acceleration in the x direction. That turns into minus mu k times mg is equal to the mass times the acceleration in the x. Cancel, cancel. We get the acceleration in the x direction as a negative mu g. Alright, that's our answer. Note, this is actually a constant value. I'm going to say this in the next couple of videos. If the acceleration is constant, we can use our constant acceleration equations for kinematics. If it's not constant, so like if I think about this right now, we have the acceleration due to gravity, that's a number, 9.81, and we have a coefficient of friction, which is just a number. It was 0.6 in this case. That gives us just a number back. It's not a function of time, it's not a function of position, it's not a function of anything, it's just a number. So you can use your constant kinematic equations for this. And what they want to know how far it went. We have no time involved anywhere, so that kind of makes me go to v final squared is equal to v naught squared plus 2a delta x. And we can rearrange that for our delta x. Delta x is equal to v final squared minus v naught squared. V final will go to 0 because they want to know when it comes to a stop. And then we have 2 times the acceleration, but we have the acceleration right there. Put in a minus mu times gravity. So on a dry surface, we can calculate this to be about 8.5 meters. That's how long it took to slam on the brakes and come to a stop. The next says, what if it's icy? And they say mu turns to 0.1. Well, everything we did works perfectly fine We just need to put a 0.1 in for right there. And if we do that for part 2, our delta x comes out to be 51 meters. Look at the difference in that. One slid got almost an order of magnitude more. An order of magnitude, if someone ever says that, by the way, means a power of 10. So 10 to the first. 10 is an order of magnitude bigger than 1. 100 is an order of magnitude bigger than 10. And you can say like things like 51 and maybe another number, 72. They're on the same order of magnitude because they're within the same power of 10. Okay, now the next part was, what if we put this on an incline? And they say 5 degrees. I'm going to draw it a little bit more drastic. And I'm just going to represent the car as a block. 5 degrees is our angle. And let me write that somewhere else. Theta is equal to 5 degrees. We need to do a free body diagram on this. We need to say, okay, mg is going down. We have some normal force going up. We need that normal force when we're dealing with friction, so don't neglect both components, right? We need the component of the weight down from the normal force, and then the component of the weight down the incline. This one is our mg sine theta, and this is mg cosine theta. Excuse me. Now we have a frictional force going to the back, and if we wanted to find the acceleration down the plane and then figure out how far it went before it stopped, well, we just need to sum the forces just like before and use kinematic equations. Okay, first of all, we can say if we do the forces in the perpendicular direction, that there's no acceleration in that direction. It's not moving off the surface or going down, right? So we can say that the normal force minus mg cosine theta is equal to 0, or the normal force is equal to mg cosine theta. All right, we'll need that later for friction. Friction is equal to mu k times the normal force. So if we're dealing with friction, even if there's no motion in that direction, we still need to analyze it. Look at the forces. It's in static equilibrium in that direction, but we still need to free body diagram Newton's second law. Okay, now let's look at the forces in the parallel or down the plane direction. I have a positive mg sine theta right here, and a frictional force going backwards. And that's going to equal the mass times the acceleration down the plane. We can substitute that the frictional force is mu times the normal force. And then we can also substitute our findings of the normal force, which was mg cosine theta. So copying down the rest. Okay. And this term mg sine theta. Okay, we got it now. We've got the acceleration. Turns out the mass does not matter. You can cancel it from every term. And we get an acceleration down the ramp of g sine theta minus mu g cosine theta. So we could factor out the g. sine theta minus mu cosine theta. Alright, there's our acceleration. They did want to know how far does it go before stopping. Keywords, stopping means v final equals 0, so we can use the same kinematic equation before. This is still a constant value, this whole thing. It is a number. Every one of those things is not changing with time or position. It is just a number, right? Gravity is a number. The sine of the incline is a number. Mu is a number. And cosine of theta is just a number. So that means we can use the constant acceleration equations. In the next video, or in one of the next videos, I'm going to show you why I keep emphasizing this. We can use constant acceleration equation. We can crank this number out actually real quick. I know y'all like the numbers. This comes out to be a negative 0.122 meters per second squared. For the other accelerations, I don't have my calculator on me. But we took v final squared is equal to v naught squared plus 2a delta x. And we rearranged this for delta x and said delta x is equal to v final minus v naught all divided by 2a. Alright, delta x in this case, using our acceleration that we just found, or this value right here, comes out to be 400 meters. Alright, we looked at a case with rubber tires on a dry horizontal road, got 8.5 meters. Oh, I don't know what just happened. So 8.5 meters was dry and horizontal. Then it was 50 something, I think 51 meters for a icy horizontal road. And then put that thing on a 5-degree incline. Look, 5 degrees is nothing, y'all. This is the reason I didn't draw it, because it wouldn't be very easy to make a free body diagram from. I can barely get there we go. 5 degrees is nothing. And there's our 0. So just a little bit of a hill, and we went up another order of magnitude. Right? We went 50 to 400 meters. Be safe out there. When it does happen to snow every 10 years or so. I know I actually went around driving a couple years ago, or last year when it snowed. Got stuck in it a couple times. Alright, it's another time. Have a good one.